Welcome back. Our final lecture on electric circuits that I'm going to be doing deals with parallel circuits. And parallel circuits still follow the same equations as we did earlier with Ohm's law and the power calculation. And if you compare this to the last video, there's some notable differences. One thing is that parallel circuits, by definition, have multiple paths for electricity to flow. I've got one drawn over here, and you can note that the battery or power source of 12 volts, which is the same as I used in the series circuit, is over here on the left. But then I've got one branch here, another branch here, and finally a third branch over here. I've got an ammeter located here to measure the current going through the main part of the circuit. And by the way, one thing I didn't mention before, a lot of people think that the battery provides charge. The battery does not provide charge. It provides an energy to push the charge. So it's not that charge gets used up as a battery wears out. It's basically that that difference in energy or potential difference across this gets used. And that even might be a little bit simplified right there. But I want you to understand the charge that flows through here also flows through the battery. It's just the battery gives that charge extra energy to push it along through chemical processes most of the time. All right, so I've got an ammeter also designed to measure the current through this branch, an ammeter to measure the current through this branch, and an ammeter to measure the current through this branch. I've only got one voltmeter in the circuit, and the reason for that is going to be listed down here. So, big idea, multiple paths for electricity to flow. This is the other thing that's tough for students to get their heads around. How we determine total resistance is quite different in parallel circuits. And I'm going to need you to practice this a bit because it's easy to make mistakes. So essentially what ends up happening is the more branches we have, the less resistance that we have. Now you might think, well, wait a second, that seems a little odd. Well, let's go back over here. I'm going to use a small whiteboard to hide parts of this circuit. If I think of a very simple series circuit over here, which only has a 12 volt power source and a 3 ohm resistor, 12 volts divided by 3 ohms gives me 4 amps of current. There would be 4 amps of current going through that particular branch. Well, now, if I have a circuit with only a 4 ohm resistor, like this, 12 volts divided by 4 ohms in that particular series circuit will give me 3 amps of current. Well, now if I have both of them, and they're independent if you notice, the current that goes through this branch does not travel through this resistor. So these are independent loops of the circuit. And each loop has 12 volts across it because voltage is a potential difference. And in any loop of a circuit, you've got to use up all the voltage. So really what I've got here is I've got current going through here, more current going through here. Combined, I would have 4 amps through here, 3 amps through here, 7 amps. And so that means if I think about my Ohm's law, V divided by R, 7 amps is equal to 12 volts divided by a much smaller resistance than if I had only a 3 ohm resistor or a 4 ohm resistor. Same way over here if I only had this 5 ohm resistor. 12 volts divided by 5 ohms would give me 2.4 amps, and that would be the current if I had a series circuit with only that resistor. So as I add more and more and more branches, I actually get less and less resistance. An extreme example of this would be if I added another branch over here. And let's say this branch has a resistor with 1 bajillion ohms. That's a lot of ohms. So if it's that many ohms, would much current pass through it? No. A tiny little bit of current would pass through it. But when I think about the total current in the circuit as being the current going through this branch, plus this branch, plus this branch, and now plus this branch, even a little bit of extra current in the whole circuit means my resistance is a little bit lower. I can look at that by rearranging Ohm's law. Now, algebraically, resistance is equal to change in voltage divided by current. So if my current gets a little bit bigger and I've got the same voltage, my resistance has to get just a little bit smaller. So any additional branch is going to end up giving you less resistance. That's, like I said, that's a tough concept for people to understand. So we're going to go back to this circuit now. So multiple paths for current to flow, this is how we can determine the total resistance by adding the reciprocals and then taking the reciprocal of that, which is, again, mathematically something you want to practice. Current in each branch adds up to the total current. So the current in this branch plus this branch plus this branch should add up to the total current provided by the power source. And finally, and this is the part that's easier about parallel circuits, is the voltage difference or potential difference across each branch is the same. And in fact, that's why I've only included 1 voltmeter in the circuit over here. All right, so let's go and try to solve things. Normally we try to solve the total resistance first. I'm going to have to do a decent amount of math to do this. So when I add fractions here, and you've got to make sure you know how to put this in your calculator, this would be 1 over the total resistance is equal to 1/3 plus 1/4 plus 1/5. Now you can have fractions in the fractions here. So this could be like 3.5 ohms, 4.8 ohms, 5.9 ohms, stuff like that. For what we're doing right now, we're going to keep it pretty simple. And if you're not sure how to add fractions, you need to think about that. I know that seems kind of silly, but a lot of people forget because they've done so much more math than that in recent years. The way I always like to think about it is like pizza pie. So if you had a circuit with 3 resistors that were each, say, 12 ohms, you want to add them, you go 1/12 of a pizza pie plus another 1/12 of a pizza pie plus another 1/12 of a pizza pie equals what? Well, and a lot of people will say 3/36 of a pizza pie. Nope. 1/12 plus a 12 plus a 12 is 3/12 of a pizza pie. You get a more pizza pie. So that reduces down to 1/4. 3/12 is the same as 1/4, but 1/4 wouldn't equal the resistance of the circuit. It would equal 1 over the resistance. So I'm going to show you how to do that right now. So if I end up having 1/3 plus 1/4 plus 1/5, and I put that in my calculator, 1 over 3 plus 1 over 4 plus 1 over 5, it gives me a number that's not nice and pretty. So essentially I get 1 over RT is equal to 0.783 ohms, 1 per ohm, I guess. Well, that tells me 1 over this. It doesn't tell me the value itself. Now there's a couple ways you could do that. You could think of this as being over 1 and now cross multiply, or you could simply take the reciprocal of this value, which I'm going to do, and push that 1 over x or x to the -1 button in the calculator one last time, and I get 1.28 ohms. So that's the resistance of this circuit. Notice the resistance of a circuit that's a parallel circuit is lower than the resistance of the least resistive element. So in other words, this has to be lower than 3 ohms. Each additional branch, remember, lowers the resistance of the circuit. So I'm going to put this up here as 1.28 ohms. And now I'm going to go and try to figure out the total current. Well, that's actually pretty easy, because if I go back to Ohm's law, I know that the circuit has 12 volts. I know that my circuit is 1.28 ohms. So 12 volts. And that comes out to like 9.38 blah, 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 which rounds to 9.4 amps. It's a lot of current. What about the current for each of these branches? Well, in order to do that, I need to figure out the voltage across each of the branches. But this is the nice part. So if you remember, the voltage or potential difference across each branch is the same. So that means the voltage across this would be 12 volts. The voltage across this would be 12 volts. And the voltage across this would be 12 volts. It's sometimes called potential difference instead of voltage. So in some ways, you could think of this as being like at the top of a 12-meter hill, and this is the bottom of a hill, or 0 meters. So if you think about potential energy, it's like you're going from the top of a hill down to the bottom, whether you go this path or this path or this path. So the flow will be different in each of these paths, but the difference in potential energy per charge, or voltage, won't be. So in fact, I don't have to do any math for this. I know that the voltage across that voltmeter is going to be 12 volts. Now, one sneaky thing might happen is if I put the voltmeter here, there's actually no voltage across that. Why? Well, when I go back to Ohm's law, one of the ways I can use that is V equals I times R. So the voltage in each branch is equal to the current through the branch times the resistance in the branch. But if my voltmeter isn't across a resistor, it does take no energy to get through this particular spot, what's called an ideal wire, ideal meaning zero resistance. So the voltage across each of these branches is across the resistor in the branch. But all of them would have 12 volts. So now, the last thing I can do is go and figure out the current through branch in here, and here, and here. So I'm going to say A1, or the current through A1, is 12 volts, because that's the voltage across this branch, divided by 3 ohms. I think I mentioned before that's 4 amps. Here, the voltage, or the current A2, 12 volts, 4 ohms, that's 3 amps. Ugh, kind of messy here. That's I'm going to move this. That's a little better. 4 amps, 3 amps. Voltage through this branch, A3, 12 volts, divided by 5 ohms, 2.4 amps. Now, this gets back to the part that I mentioned earlier. The current through each branch in a parallel circuit should add up to the total current. So let's check to see if that's correct. I had 9.4 amps here when I simply took the total voltage provided by the power source and the total resistance I figured out earlier. Here, this current through this branch is 4 amps plus 3 amps, that's 7. Through this one is 2.4, 7 plus 2.4 gives me 9.4 amps. Same answer. So that actually is really nice as a way to double check things. So hopefully this helps understand parallel circuits, and again, I'll give supplemental information about that from the physics classroom.